Next, I'm going to show you an example where a multi-categorical variable interacts with a binary variable. And I'm using this part of the regression interactions.r code file. So the goal here is to see what happens when we have color interacting with material. Color is a multi-categorical variable, a factor with 4 levels. And in the previous session, we saw what happens when we use a factor that has 4 levels. R creates 3 contrasts automatically to represent the values of that factor and includes them in the regression model. So when we call summary of LM with this formula, price as the response variable and color interacting with material as the predictors that will give us color, material, and their interaction, we get more than 3 slopes. We get an intercept, 3 indicator variable slopes for color, the slope for material, and 3 interaction terms representing the interaction between each of these indicator variables and the material variable. But otherwise, the interpretation is very similar. We might, for example, focus on the slope for material in this model because it represents the difference between plastic and metal robots in the reference category for color, the point where all 6 of these other predictors are 0. For the robots that are painted black, the metal ones cost $19.43 more than the plastic ones. And 95.83 represents the fitted value of the model for the black robots made of plastic. In other words, the average cost of the black robots that are made of plastic, because this model that has an interaction between 2 categorical variables fully accounts for all of the means that you would get if you calculated the mean price for each combination of those categorical variables. In this case, there are 8 combinations because there are 4 colors and 2 materials. So I'm going to rerun the model where I've explicitly specified that the reference category for color is black and the reference category for material is plastic. This is the same as the version of the model we just ran, but for the sake of completeness, I want to show it this way. And we see that the metal robots cost $19.43 more when they're painted black. But we might also want to interpret the slopes for the indicator variables for color in this model. And that interpretation is just like when we included a multi-categorical variable like color in a simple linear regression model, except that now they're all interpreted at the reference point for material because there's an interaction between color and material in the model. In other words, the reference point for material is plastic. So color blue represents the price difference on average between blue robots and black robots for the plastic robots. In other words, the difference between blue plastic robots and black plastic robots was $5, and that difference was not large enough to be statistically significant. The difference between green plastic robots and black plastic robots was $2, not significant, and the difference between red plastic robots and black plastic robots was negative $1.2, and also not statistically significant. All of these are color comparisons among plastic robots, because plastic is the reference category for material. But I can change the reference category for material by re-leveling the material variable, so now we will get an indicator variable where metal is 0 and plastic is 1, and fit the model again. And these color comparisons represent comparisons between each of these colors in the reference color black for the metal robots. Blue metal robots cost $1.29 less than black metal robots, not significant. But green metal robots cost $13.74 less than the black metal robots, and red metal robots cost $16 less than the black metal robots, and both of those discrepancies are statistically significant. So it seems that green and red robots were systematically undervalued relative to black robots when they were made of metal, but not when they were made of plastic. So I have had comparisons between each color of robot and black for the metal robots and the plastic robots separately, but perhaps I would like to do additional comparisons where I change the color reference category. For example, I never compared blue robots to green robots, whether they're made of metal or plastic. So if I change the reference category for color to blue and then repeat what I just did, then I will get comparisons between green robots and black and blue robots for the plastic ones and the metal ones. So here I can see that green robots were a little bit less expensive, not significant than the blue plastic robots, and the red ones were a little bit less expensive, not significant than the blue plastic robots. But when I switched to metal robots, green and red were significantly less expensive than blue. Black was not significantly different from blue. And there's still one comparison missing, the comparison between green and red. So here it is for plastic robots. I've just changed the reference categories to green and plastic, and green and red were not significantly different for plastic robots. But when I switched to metal robots, green and red were also not significantly different. And the conclusion here is that blue and black robots appear to be significantly more expensive than the other colors of robots as long as they're made of metal. But when the robots are made of plastic, none of the colors are significantly different from each other. Finally, I want to talk about a multi-categorical variable interacting with a continuous variable, and I'm going to use color and battery life for that purpose. So here I've fit a regression model where price is the response variable, and I've got color interacting with battery using the asterisk to specify that I want the full interaction. And here I might be interested in the slope for battery life. This will tell me about the relationship between battery life and price at the reference value for color. Perhaps to be explicit about it, I will rerun this having explicitly releveled color so the reference category is black, just for the sake of symmetry when I'm going to relevel it in the three other ways in a moment. And I can see that the slope of battery life is 1.87, and it is statistically significant, meaning that for black robots, longer battery life is associated with a higher price. For blue robots, with blue as the reference category, longer battery life is also associated with a higher price, and it's statistically significant. For green robots, longer battery life is also associated with a higher price, and it's statistically significant. But this slope is 2.56, which seems to be much higher than those other two slopes for the black robots and the blue robots. And for red robots, longer battery life is associated with higher price, but the slope is 1.43, which is more similar to what it was for the black robots and the blue robots. So I might want to understand what's going on here by asking questions like, was that slope for the green robots actually significantly stronger than the slopes for these other colors of robots? Does battery life matter more for the price when the robot is painted green than when it's painted any other color? To answer that question, I might want to focus on the interaction terms in this model. This interaction term here represents the difference in the slope of battery life depending on whether the robot is green or the reference category of color, which is red here. In other words, the slope for battery life is significantly stronger for the green robot than for the red robot. But the slope for battery life is not significantly stronger for the blue or black robots compared to the red robots. Here with black as the reference category, I can see that the slope for battery life for the black robots, 1.87, does not significantly differ from the slopes for any of the other three colors of robots, although it is close when we're looking at the green robot. The slope for the green robots is 0.69 stronger than the slope for black robots, and it is almost statistically significant. When I change the reference point to blue, the slope is 1.52, and I can see that it is not significantly different from the slope for the black and red robots, but the slope for green robots is significantly stronger than the slope for blue robots. When I change the reference point to green, I can see just what I already knew, that the blue robot slope was significantly weaker than the green robot slope, and the black robot slope was weaker than the green robot slope and not quite statistically significant. And the red robot's slope is significantly weaker than the green robot's slope, which makes sense because the slope between battery and price for the green robots is 2.56, which appears to be much stronger than these other slopes that are around 1.5 instead of 2.5. And for completeness, here's the slope for red robots again, and we see that the green robots are significantly stronger relationship between battery and price, and these other two colors were not. So it seems like we have some indication here that for green robots, battery life matters even more for the price. Everyone prefers robots with longer battery life, but when those robots are painted green, battery life is even more imperative in determining the price, although the difference between the slope of battery life for green robots and black robots did not quite reach statistical significance. If this was a real data set, I might be tempted to look into some clues about why this might be the case, such as maybe the green robots are marketed as being environmentally friendly or something like that.